Hello everyone, myself Saravanan, a postgraduate student in Embedded System Technology from M.Tech, Dr.RR and Dr.SR Technical University. My project is about IMU based indoor mobility alignment and its 3D cloud point generation. The project was guided by Dr.S.Baskar, Professor of EEE Department from M.Tech University. The goal of the project is to develop an error-free positioning in indoor environment. For this, the approach here we have used is an IMU based technique which gives more accuracy in an indoor environment. Before going to my project, I would like to give a brief study which I have done under this area. And Dr.RR James et al. Says in his paper he have used various techniques like LSP, local positioning system, and PDR, pedestrian dead rocking. He explains an estimation of a person positioning in an indoor buildings. Different methods like IMU, IEZs are compared with this in this paper. And another paper, and Hartman describes a system for 3D positioning tracking with an IMU measurements and position correction with video tracking systems. And in an Hendrik Hellman, DC magnetic signals based indoor localization systems have been used with an infrared based indoor positioning technologies such as UWB, wide WLAN, ultrasonic PR infrared sensors are limited by distributions and error caused by building objects. These are the paper which I have used for a reference. In a proposed technology, the core concentration of the paper is an IMU based technology for indoor positioning, and we have used a LabVIEW environment. By using LabVIEW software, we can view the subject and exact position in a 3D point where it is exactly placed in indoor, and an object movement and a direction and step movement in indoor can also be monitored in the LabVIEW environment. The software we have used is an MPLab IDE, LabVIEW, and Eagle software, and an ORCAD. And LabVIEW here we use in V8.1 used for PIC microcontroller programming for compiling, debugging, and executing. And LabVIEW here we use in LabVIEW 11.5 version and is used to create a monitoring panel with a serial communication link established between monitoring and the RF receiver unit using serial resource in the LabVIEW, and Eagle for an PCB design and ORCAD for schematic design. And an hardware requirements we have used is an IMU PIC 18F series, RF transceiver, a PIC2, a power supply, USB, and LCD display. The IMU here we have used is an GY80 IMU with gives and 10 degree of freedom, and PIC 18F series which is some 40 pin IC with various specification, and an RF transceiver as a Tarang model transceiver, and PIC2 as a debugger, and then power supply used as a battery which is most efficient with which is a 12 volt battery, and USB for interface between RF transceiver and a PC, and LCD display for displaying and attitude, direction, and other stuff. And this is a moving unit block diagram and a receiving unit block diagram. In a moving unit, we have used an IMU with a combination of several sensors like a gyroscopic magnetometer, accelerometer, and barometer. This combined IMU unit is connected to microcontroller along with LCD display and RF transceiver. And in a receiver unit, we have used an USB interface between a PC and a receiver unit. In a moving unit is placed with object. A receiver unit is connected with a PC. A PC as a lab environment for monitoring. And IMU here we used for a 10 degree of IMU. It measures the velocity, orientation, gravitational pull using combination of several sensors like gyroscopic, magnetometer, accelerometer, and barometers. The gyroscopic sensor for acceleration, it is a 3-axis MEMS gyroscopic IC. which iterate the rotation rate of an XY axis, such as a roll pitch yaw. When gyroscopic IC rotated about any of an sensor's axis, the correlative effect caused the deflection that detected by the capacity peak off. The resulting signals is amplified and demodulated and filtered to the produced on voltage that proportional to the angular rate. The application used in for gyroscopics are for gaming, 3D remote control applications, and magnetometer for navigation purpose. It is also 3-axis digital IC compass. It used for navigation measurement. It can enable at a 0 to 2 degree compass. It is a more accurate and an 8 compass which has a magnetic field environment, and applications here as mobile phones and auto navigation system and notebooks. And an accelerometer for angle measurement. It is on 3-axis with high resolution measurement up to plus or minus 16 G, and a barometer for pressure measurement and digital pressure sensors. Here we have shown two different sensor positioning, and figure A shows an individual output of the sensors, and figure B shows an IMU position of an object. Here the map shows the difference between IMU output and an individual sensor output. Individual output of the 4 different sensor with positioning reading and multiples the point in the graph is shown in figure A. To make those output into a single point, it requires a more mathematical calculation as well. It is more complicated, but in a figure B it shows an IMU positioning of an object. IMU unit gives a combination output of 4 sensors and into a single point. It makes positioning an indoor environment with high precision point in comparatively easy manner. An RF transceiver here uses a terrain model which has a frequency range of about 2.4 to 2.48 GHz, and an RF data rate is about 250 kbps. The serial interface data rate is about 1,05,200 baud, and an acknowledgement mode communication are used, and analog to digital conversion and digital I/O lines are supported. And PIC 18F45K double series is used here, which has a 40-pin low voltage microcontroller and a flash memory of about 32 KB, and an EEPROM data memory of 256 KB, and SRAM data memory of 1536 bytes, and 36 IO pins are here, and timers like 3 8-bit timers, 4 16-bit timers, and ADC converter with 10-bit 13 channels are used. And simulation results here is, this is a LabVIEW based 3D plot for indoor pedestrian positioning monitoring panel. It is used for positioning an object. The monitoring panel in LabVIEW has a 2D plot, 3D plot, and free space shows for free movement area, and IMU signals are given virtually instead of IMU as an hardware, and step movement and direction can be changed manually. The 2D plot graph is used, which gives an XY axis graph, which in X as an attitude and in Y as an direction, and in a 3D plot which has a three-dimensional view of an indoor position. And an algorithm we have developed is, first we have to power up the IMU model with 3.3 volt to 5 volt power supply. Then initializing pedestrian position, check whether the pedestrian is in motion. If no, IMU is still in idle state, then reset and initialize the pedestrian position. If yes, measure the attitude, direction, acceleration and number of step movement using sensors. Sensors values are digitalized using ADC and transmitter. will send the data, check the transmission. If no, blink in green LED transmission is error and reset the system. If green LED blinks, RF transceiver will collect the data. RF receiver is connected to the LabVIEW serial communication port with an USB cable. LabVIEW monitoring panel displays the position of the pedestrian from the collected data. Direction, orientation, number of steps, X-plot, 3D plot and the path traced are displayed in the LabVIEW panels and hardware output. In figure here shows a LabVIEW based indoor pedestrian monitoring panel in a minus 0.08 direction with 47 steps, and in a figure B which is coming below, it shows in a direction of about 47 degree with a step of 7, and here in monitoring panel we have to connect with an RF transceiver with an whole kit, and here we shows the, oh my god, the port number has been displayed here as an COM15. After enabling this port, the initial position of an IMU is starts at 0 and with a variable direction, and direction and attitude can also be displayed here. The x-axis and y-axis also shown, so number of steps as shown here. This is a free space of an object, and it is a spider web plot, and it shows and corresponding LCD display in an IMU transmitter module, and Y shows an direction and A shows a number of attitude, and number of steps has been shown here. This LCD display is placed in a transmitter section which has been placed with a moving object, and the precision, direction and attitude is identified here. The two different direction of pedestrian position as shown as in a figure A and figure B, which is coming next. An LCD display is in a moving unit display the information about the pedestrian positions. This is a figure A which shows a different direction and different steps from the previous one. Here it shows a minus 124.8 degree with 7 steps. The direction, attitude and steps has been changed, and we have checked with various degrees and directions, and the corresponding LCD display for a previous step angle has been shown here. This is an overall mobile IMU transmitter module. This has a battery which is connected to a microcontroller, and an LCD display which is connected in a moving object, which gives an information about the object, where it is and direction, number of steps, and it is an IMU unit which is a combination of several sensors, and this is a tap sensor. This tap sensor here which gives the step movement for each tap, and it is a transceiver module which is connected with an FTD cable to an PC, which is not shown in this figure, and this is an overall PIC microcontroller, and this is a transmitter module, and for each transmission the green LED gets blinking. This tap sensor can be placed in a foot for an ideal step movement can be calculated. Conclusion for this project is in this project with IMU module based positioning, a person orientation or a degree of a direction with accuracy of 0.1, which is far better than a previous technologies. A previous method does not have a perfection and accuracy when the subject pointing at an indoor. The previous technologies like GPS technology, RFIDs, those technology can only position the particular building where the subject or an object is. It cannot give the exact position of an object in an indoor environment. So to overcome those problems, we are going for IMU based indoor positioning. As step taken by a person sense using highly sensitive touch sensor infrared with interface with the barometric meter produce and vivid and vivid a trajectory path is obtained in a monitoring panel using touch sensor interface with barometer. And indoor mapping creation is difficult. Still, it's a very challenging. An IMU model should be incorporated with a camera and other highly sophisticated image processing unit. By this system, we can localize the position of the pedestrian inside the building. Here, the reference we have used, several references we have used here. And my conference and publication works. First one is an IMU based indoor mobility alignment and is 3D cloud point generation. Is a paper on same project. It published in International Journal of Science, Engineering Science and Innovation Technology in volume 4 on March 2015. And second one is an auto comfort wheelchair system for physically challenged. I propose a wheelchair system which works under an hand movement recognition with accelerometer. This is published in an proceedings of IEEE, second International Conference of Knowledge Collaboration in Engineering on March 2015. Third is an FPGA implementation on smart card based license management using iris scanning. It's published in proceedings of first IEEE International Conference on Science, Engineering and Management Research, November 2014. In this paper, I propose a smart card based license with iris scanning for eye security purpose. This is published on November 2014. And fourth one is an Aadhaar license management system in India using Aadhaar IDs. It is an extension works of an above paper. It published in proceedings of a Springer series of advanced in intelligent system and computing. It's published on I presented this paper on March 2015. Thank you for listening. This paper is available in ResearchGate for your downloads. Kindly find the link below. For any queries and feedback, you can mail to my inbox saravanadurai05@gmail.com. Thank you.